Good morning, everyone. Um, Today we are going to do the second lecture in environmental sustainability. First of all, I would ask that if you don't hear me, please send me a message and I'll try to sort it out. Anyway, the lecture will be recorded. I'll put everything in my page into the website, the school website. It's going to be um, easy for you to check the recording and also the slides, which I will put in the website as well. Um, If you were at the seminar, which was intended as a first lecture, and which equally I recorded and I put on the web page. Anyway, if you don't have it, feel free to email me. I would welcome you to email me also to take into account the list of the students which are following the course. After this very general information, I would like to start to clarify which is going to be our objective today, which is going to be developed over the next few lectures and which comes directly from what I was saying in the seminar. I concluded the seminar by indicating that we have a number of goals, which are 17, about sustainability, goals which were set to be completed in 2030, so over 10 years' time. The United Nations set these goals, and some of these concern the environment. Others have some connection with the environment, but concern more social or economical questions. Like the first one is abolishing the poverty. And of course, this has a connection with environment, and it's not even a loose one, but because we need to abolish poverty without harming too much the environment. For example, what we want to concentrate on is the goal number 12, which is responsible consumption and production. It is a big objective to get to responsible consumption and production. Therefore, we will concentrate on one or two, rather two interconnected sub-goals, sub-objectives, which are in our view, which we can sort out, because sort it out alone, the responsible consumption and production is going to be quite philosophical and may involve a number of different sectors and so on. We concentrate on materials, energy, and pollution. So basically, the example of responsible consumption and production, as it is stated in this slide, is the fact that we aim to substitute oil-based plastic, to replace oil-based plastic with bio-based plastics and bioplastics. And since plastics is a waste, becomes a waste, and it becomes a waste quite quickly if it is single-use plastics. So you use it once and no more, then you throw it and it becomes waste. The idea of circular economy is that waste shouldn't exist anymore. That means that we could either find a way to reduce waste, therefore a way to reuse a material or reuse an object, for example, packaging, for example, a plastic bottle, we could reuse and therefore elongating its life. Remember that whatever your subject of study and whatever your problem, a longer life for materials and objects, it's the first requirement for sustainability. If you make the life of materials and objects longer, then you are more sustainable. Of course, if I ask you if bio is better than oil-based, you would probably 99% of you would say yes, bio-based plastics it's better than oil-based. And bioplastics is even better than this. I would clarify what is the difference between bio-based plastics and bioplastics. Bio-based plastics means that we produce the same plastics that we use to have now, like polyethylene terephthalate, and so on. So the same plastics, we produce it with raw materials that come from agriculture. For example, with oils, some kind of vegetable oils or plant oils. Instead that with oil coming from extraction. So petrol, basically, and other similar fractions which are extracted as hydrocarbons and so on. On the other side, bioplastics means that we don't produce the same plastics, but we produce other plastics which are based on mainly on polysaccharides, on derivatives from sugars, from glucose, like starch or cellulose, or we produce them from proteins. So we get other plastics. So to simplify very much, I would say that bio-based plastics means you make the same plastics with bio-based materials. And with bioplastics, you make other plastics which are really bio. The consequence is that bioplastics are not biodegradable normally, and bioplastics are biodegradable. If we want to reduce waste, we could consider using waste to make other materials, for example, plastics, and for example, in a field which is very impacting, which produces a lot of waste, which is packaging. If we look at the experience in our houses about differentiated waste collection, we find out that most of the waste is packaging. We will go into more details in the next few lectures about packaging, but basically packaging is something that it's aimed to contain liquids or solids or food. And this action of containment is essential for our life. But that means also that after we have emptied the packaging, we most of the time throw it away. Then it becomes waste. Then it is a problem. Then it's not a case that it's not just for adventure that the first directives that were promulgated by the European Union, the United Nations, and so on, concern packaging, reducing waste from packaging. That diagram, which I show below, basically says the same thing, and I have shown it already in the seminar. Basically, there are 4 types of plastics. the conventional ones, which are bottom left. Then we have other kinds of bioplastics. The term bioplastics is extremely confusing. And I would discourage its use, although I feel that it works very well from a media point of view. I would discourage its use because you mean by bioplastics three different types of plastics. Bio-based plastics, which is the more correct way of saying things, so which are the top left, which are based on renewable raw materials like plant oils, but they are not biodegradable. Then we have bottom left, the ones which are obtained from materials, from biological materials, and they are biodegradable and also bio-based. But there is also a fourth family, which is the one which you find bottom right, and which is composed by these kind of plastics, which are produced by oil extraction, so by hydrocarbons, but they are biodegradable. So they are produced by oil, so therefore the raw materials are not bio. Like to be clear, the raw materials are not bio, but they are biodegradable and in the end. The main member of this family is the polycaprolactone, which is the PCl, which is of longer, acquiring a lot of importance now, especially for medical application and so on, apart from its cost, which is still important. But anyway, there is also this possibility that you use oil, extracted oil, and you produce something which is biodegradable. So it is confusing. I can understand that. But this is the war we want to win. And basically, this is again the diagram with the addition of some more members of this family, the different families. Top left, bottom left, you find the conventional plastic. Top left, you find again the conventional plastics, but produced with biological materials, so with from agricultural materials basically. Because, for example, an example which illustrates you the question is that to produce polyethylene, you need to have oil. That's what you would think. But there is another chemical way to produce polyethylene, ethylene and then polyethylene. You can obtain ethylene from ethanol. Therefore, from ethanol, you produce them from sugars. This top left family started to develop, especially in some countries, which have lots of sugar derivatives, for example, because they have sugar cane. This is the case of Brazil, for example, but they don't have oil, extracted oil. They don't have much extracted oil. So they say, why not producing the same ethylene and therefore polyethylene, and therefore polyethylene terephthalate, PET, which is well known because we have water bottles and so on, by using ethanol. That means that you come out with a plastic which is not biodegradable, but the raw material is a biological material. It's a material extracted from sugar, obtained from sugar, and not from oil. Then the so-called bioplastics, which are the most properly called bioplastics, are the top right, polylactic acid, and polyhydroxyalkanoate, so PLA and PHA. And these ones are biodegradable, obtained from a biological matter, biological raw material. Um, there is there are different ways to do that, to produce this kind of bioplastics, which are biodegradable and obtained by renewable raw materials, as you see from the quadrant. To get them directly from the glucose, basically we get, you know, that, for example, PLA, like the Matter B is one of the brands of PLA, polylactic acid, is produced by corn starch. That's what they say. In reality, they get corn starch, they depolymerize it, and they get glucose from that, and they rebuild the polylactic acid, they repolymerize the polylactic acid starting from glucose. Why so? Because they have the difficulty that cornstarch has variable mechanical properties depending on the dimension of the granule, the corn seed, the corn granule, and so on. Then there are other ones which are produced, for example, the solanil, which is produced by potato starch. Again, depolymerizing it, getting glucose and repolymerizing it, because glucose is always the same, it's always the same molecule, C6H12 and O6. So basically, you get back to glucose and you repolymerize. Then you have PHA. PHA is polyhydroxyalkanoate, which is instead the so-called plastic which is produced by bacteria. Bioplastic produced by bacteria, and basically is not very different from what happens into wine when it becomes vinegar. It creates some structures, and it's able to produce this kind of plastics, which is again biodegradable and renewable from renewable raw materials. Then you have the starch blends, because if you want to be more free from chemical processes, you could get starch in itself, and you can create the so-called thermoplastic starches. Thermoplastic starches, which mean that you add the starch with some plasticizer, like a glycerol, for example, and you can make a plastic. Glycerol, vinegar, and so on, acetic acid, and so on. You can starch blends and thermoplastic starch. Thermoplastic starch, which is abbreviated as TPS, it's very diffuse. Of course, into there you don't. You are not linked, you're not obliged to use corn or potato and so on. We are using whatever kind of starch to make thermoplastic starch. And so this kind of plastics, and this is good. Why this is good? Because this has the possibility to come from waste, because the starch can be a waste from the food producing industry. And therefore, it's less chemically intensive. Then we have the fourth family, as I was saying, and we have the polybutyl succinate and the polycaprolactone and other ones based always on polybutyl components, polybutyl molecules, which are biodegradable but obtained from oil, from extracted oil. What we are interested in, you can see that the situation is very complicated. And I am not sure that we will get rid of the family of the, say, the bad guy, which is the family bottom left. What we want to do is substitute the family the bottom left family with either of the other three families. I can you can easily understand that each one of these had got their advantages or disadvantages. And you see that the answer to the question I was doing at the beginning is not that easy. We could reason on that. We could investigate on whether one family is better of the other. It depends what we want to have, because we could go for biodegradability, or we could go for not consuming oil, or we could go for the recyclability, because it's good to be clear about that. If something is biodegradable, it is not recyclable. Recyclable means that we are going to melt it and get another plastics, or possibly to contribute to the production of another plastic. I could get my recyclable plastics and introduce a part of it into a new plastic. If it is biodegradable, I cannot do that because it degrades. It degrades, and therefore, what I can do, I can try to dispose of it in another way. One of the ways, the main way of disposing of biodegradable materials is compostability, which is not exactly the same thing as biodegradability. In very simple terms, compostability means a biodegradability at a faster rate. Why so? Why we need a faster rate to have compostability? Because we have to insert it into compost, that compostable plastics. After having ground it, we insert it into compost, and we want that it works at according to agricultural times. So we dig holes and put seeds in winter, and we want to have fruits in summer. That's about the question, or the contrary of it. But basically, in a few months, we need the plastics, all the previous plastics, previous bioplastics, to work in the compost. You see that this is not as simple as that, because then you have to investigate on the quality of the recyclable material or the recycled material and the quality of the compostable material. So how the question is about the same. There are different aspects, but it's about the same. We want that the recyclable plastics, once it is recycled, therefore melted, we want it to be good to participate to the production of a new plastic. For compostable material, we want that that compostable material is good enough to participate into compost, therefore to contribute to agricultural activity. Okay, that's about the presentation of the question. Then we move a step back, and we would like to understand what are our options. You may have seen this already in waste management course, but this is the frame in which we are allowed to move. So basically, if we want to realize a circular economy, we would like to prevent the production of waste. And this is what the 98/2008 directive says very clearly. In this kind of triangle, the best option is top and the worst option is bottom. Therefore, waste prevention is the best option we have. In fact, after the Directive 98/2008, the European Union has started, but in the whole world, a process has started in order to understand material by material for any single material, say copper, say steel, say plastics, how we can end waste. So there are some end of waste strategies which are starting to build. Then we can prepare for reuse if we cannot avoid the production of waste, or we can recycle. The difference between reusing and recycle, I would go into details about that because I have already spoken of that about in waste management, and it's not central to our course, but it's important to remember. Recycle means that I transform the geometry of my material. In contrast, reuse is less intensive. I can keep the same geometry, keep the same bottle, for example, and reuse it. If I recycle it, that means that I destroy my bottle, first thing. So I grind it, then I melt it, then I add to other plastics, and I make not another bottle, something else, but something less else of lower value. That means that the degradation of the material in terms of value, not the biodegradation, but the reduction of value of the material, it's higher as far as I go down into the triangle. Waste prevention means that I don't have any material at all, any waste at all. But if I have the material, it's more and more degraded as far as I go down into the triangle. Then I have other recovery. Other recovery means that I can burn the material, and composting, it's something is not considered completely in this directive, is not considered as such in this directive, because it's in between recycling and other recovery, because I cannot say that I make another material. With compostable plastic, I don't make another material. I use it in compost, which is not a material as such. Remember that in engineering terms, a material is something which is able to withstand a force. Compost is not a material in this sense. It is a matter, which is different, that it's useful for agricultural activities. So composting is not considered in this directive, but is in between recycling and other recovery. It's worse than recycling in a sense. It would be worse because I am not able to generate other material, but it's better than just burning in different ways: incineration, pyrolysis, gasification. There are different ways of burning to produce energy, but it is worse in the sense that for just this directive, that doesn't mean that compostable plastics is worse than recyclable plastics. But of course, I don't produce a material anymore. You see that it's becoming tricky. The plot is getting thicker because I was sure that bio was better, but then there are some situations, some complexities that arise. What I am sure of is that I want to avoid disposal. Disposal, that means landfilling. I want to avoid landfilling just by digging a hole and putting everything in there. That I want to avoid that as much as possible. You may understand that this directive is much more complicated than what I am saying, because in reality, I am not able at the moment to avoid landfilling, but landfilling creates a lot of problems and so on. And even plastic in some cases, it is landfilling. which can create a number of problems because some microplastics can go into water, as can leach into water, can go into the soil and can harm the agricultural activities, agricultural and animal breeding activities. And also it may eventually burn, because if I dispose it in not a proper way, it may burn and release some toxic gases and so on, vapors, etc. You may know of dioxins or furanes, which have some noxious toxic effect. Okay, having said that, we need to come back to our problem, which was sustainability. And we need to compare the options we have. We were saying that we can recycle oil-based plastics. We cannot recycle biodegradable plastic, but we can compost it. One thing I need to clarify, which is very important on this aspect of plastics, is that the plastics we are talking of are thermoplastics, because the plastics are divided into two categories, which are thermoplastics and thermosetting. Thermoplastics, basically thermoplastics melt, therefore I can recycle them. I can chemically or thermally recycle them, whilst other plastics are thermosetting. Basically, with temperature, we are applying heat. They burn, they don't melt. Like wood. Wood is not a plastic. It can be considered a composite in terms of, it's a natural composite in materials terms, but it burns. Therefore, what I can do with wood, I can only recycle wood in a mechanical way. Therefore, I grind wood, I reduce to small pieces, and I put into other wood, for example. Or I mix it with some resin. And we are concentrating on thermoplastics. Oil-based plastics we consider are thermoplastics. And compostable plastics we consider biodegradable plastics are again thermoplastics. I can also make thermosetting plastics with raw materials coming from agriculture. I can use also some kind of oils to make thermosetting plastics, but we are not dealing with it in this exposition. What I do in practice, what I've done till yesterday, even in 2008, when the directive number 98 came out, oil-based plastics were paramount. I would say 95% of applications were oil-based plastics. Apart from some cellulose acetate, I didn't have much of other plastics, of compostable plastics and so on. So what was the traditional application at end of life of this plastic? What was the end of life destiny of this plastic? Apart from the majority of plastic that was still thrown on the floor, dumped on the soil and so on, the most virtuous option was to recycle it. From a thermodynamical point of view, you know that recycle means that I lose value. I have less plastics of less value, of lower value, if I recycle. There are three options. One option which is open to all materials, which is mechanical recycling. There are all materials, whatever they melt or not, or even if they have very high temperature of melting, high melting temperatures, I can grind them and put in other materials. The options which are also open to thermoplastics, where thermal recycling and chemical recycling. Thermal recycling can be then pushed to the extreme, and then you can get chemical recycling. What is the difference? Thermal recycling, I can produce another plastics because basically I just melt the material. In terms of thermoplastics, oil-based plastics, the temperatures I get for melting are from 120 to over 300 degrees, depending on the types of plastics I'm using. So basically, I need to consume some energy. Of course, I use less energy that I'm using, for example, to melt steel, which melts around 1,400 degrees. And so that's quite a different amount of energy. But I still consume some energy. Or I can push the thermal recycling at its extreme. I can increase the temperature and I can come out with hydrocarbons. So in the end, I can come back to originating hydrocarbons. For example, with polyethylene, I could not having a melted molten polyethylene, but having a really coming back to the ethylene. Then if I have ethylene, a number of possibilities are open in chemicals from the chemical point of view. I can produce other chemicals, which is another possibility, but of course I spend more energy. So this is what was usually done. You can see in this implant, which is quite easy. Of course, I have a reactor, and I absorb lime. I absorb lime or other ceramics because you need to consider one thing that I that in what is the difference between a polymer and a plastic? A plastic is a material. A polymer, it's a chemical, and there is a difference. As always, material is whatever is able to withstand some force. So for the polymer, because always there is always some mess, some confusion in also in the media, how the media speak about plastics. The polymer is not yet plastic. I have to add something to the polymer to make it plastic, especially to control the flow of the polymer. Because the polymer, when I melt them, they tend to be amorphous. And since they are amorphous in most cases, they are not really liquid. They are kind of fluids, very viscous fluids, and I have to control their viscosity. So the way they flow into the mold and they produce the piece I want to. For example, a bottle, for example, a tray, etc. For example, a fork or a knife, a plastic fork or plastic knife. This way, I need to use, to obtain this, I need to use some ceramic. For example, calcium carbonate, for example, talc, for example, lime. And then I need to absorb it if I want to recycle plastics. If I want to get back to polyethylene, for example, polypropylene and so on. Because they melt ceramics, but at very, very high temperatures, and I don't need to really to melt them. I could reintroduce, for example, the same ceramics into reproducing plastics. But in the end, what I get out is a kind of feedstock. Feedstock, means something that I can introduce into the process to make new plastics. And hydrocarbon, that means that there is something that goes away as vapors and so on. and I still produce some kind of hydrocarbons. It's which I can so ethylene, not polyethylene. For example, if I'm using polyethylene or propylene or whatever, and this can be used to produce chemicals. If I push it to an extreme into chemical recycling, I don't get much of feedstock anymore, but I get just basically hydrocarbons, and I can use it in the chemical industry, not necessarily for to produce plastic. But of course, I consume more energy. But in some cases, it may happen that the polymers are precious, and I prefer to reuse them into the chemical industry. This is not often the case with ethylene or propylene, which are not that expensive, but might be the case for other hydrocarbons, which are usually used for plastics. For example, this is might be the case for furans, styrene, and so on. But without going into all these details, it's important to remember that there are at least three types of recycling. And it's important to bear in mind, coming back to sustainability, that each one of these stages we always start from mechanical recycling. Then in thermoplastics, of course, we can go further. And also for some metals, we go further, for example. For wood, we need to stop at mechanical recycling because they don't melt. Mechanical recycling, thermal recycling, and chemical recycling all consume some amount of energy, which goes into the bill, into the account we need to make if we want to understand whether a process is more sustainable than another one. So coming back to your question or to my question at the beginning, it's not that bio is better. We need to take into account the consumption of materials, the consumption of energy, and the different pollutions that every stage of our process generates. This is a process which is called life cycle analysis, and which gives you a model of all this impact. We are concentrating on the last side, on the final phase, I would say, which is end of life. But of course, there is an environmental impact for production, for pre-production, and from service. When I mean pre-production of plastics, if it is oil-based plastics, it is the environmental impact from the production of oil, from oil extraction. Pre-production, for example, for biodegradable, compostable plastics can be, for example, the production of corn and of corn starch, which is the raw material. Of course, I may consume different amounts of water. I may be involved into different temperature heating. This is different from oil than from starch. You can understand that. But the important matter is that it's always a question of comparison. All the directives about sustainability want to implement the best practices. The best practices means that it is the practice which is less impacting. For example, an example which comes from the last few days is that most of us are locked at home because our government and the authorities, the scientific authorities, think that the best practice is staying at home instead that going around, because it would lead to less casualties, to less expenses, and to less problems in general terms. So it is more sustainable. This might be questionable, as always. There is someone else who says that you shouldn't stay locked at home, but you should carry on with some activity. That some people should carry on with some activities. And this is applied to the context, needs to be applied to the context, because also in this case, there are some factories which are locked down, some other factories which haven't. And so they may consider that it's more sustainable for their workers and for the environment in general that it's sustainable to stay open. It depends from what they produce, it depends on what they produce. But it depends also on the final amount of casualties and of economical losses they have. So that's how sustainability works. It's always a comparison between different possible options, which might be two, which might be more than two. You have seen the plastic quadrant. We have 4 options and a lot of sub-options, because I may select different, for example, oil-based plastics. The impact of polyethylene is not the same as polypropylene. So there are 4 main options and a number of sub-options. That looks complicated, but in the end, a choice is also to select a limited number of reasonable options between which I can compare. Okay, what is the situation instead with compostable plastic? It's important to give, first of all, some definitions. First of all, degradation. These are definitions from the latest version of the STM, which means American Society for Testing and Materials, sorted out in 2019. You can see the 19 in the standard title. So degradation, it's an irreversible process, which explains why we cannot recycle if we degrade. It is irreversible, and of course there is a change in material structure, and you get some fragmentation and depolymerization. So basically, degradation is not biodegradation. These are not synonyms, because degradation can occur also into oil-based plastics. All the oil-based plastics, say polyethylene or polypropylene, polystyrene, and so on, can degrade. For example, if you leave a polyethylene container under the sun, you can get some degradation. Or if you apply an acid, you can get some degradation. This doesn't involve any application of microorganisms and any action from the nature in itself. But it is important to be clear that degradation is not yet by the biodegradation. You need to have a biodegradation, not just any degradation, because yes, because you can consider that the polyethylene, for example, a polyethylene tray can be degraded into the sun, being exposed to the sun, and so it comes down as microplastic. It can break into fragments, but you are, of course, not able to apply it, even if it is. This would be. In some cases, this can be quite fast. For example, you put chemicals, and some chemicals, some acids, and it can degrade, but it wouldn't be compostable in any case, because it would be inert, if not toxic, when put into compost. So biodegradation, it is degradation obtained by a clear biological action. It's not just an action of some chemicals or by the sun, but there is a precise biological action, which means also another thing, that a clear biological action means that you have a time in which that takes place. So you are able to measure the time, and you are able to measure the production of carbon dioxide, water, methane, biomass. There is also a definition for biomass. Biomass is something that has an interaction with biological elements. This is the definition of biomass. It is also quite strict, in the sense that you could produce energy from biomass, and this can be quite interesting, provided that this is really biomass. One of the problems we found out, I would explain better, is one of the problems you found out with incineration, for example, is that biomass tend to incinerate at quite low, reasonably low temperatures, provided it doesn't contain ceramic materials, for example. You may consider that you can collect also into your organic bin. You can collect, for example, clam shells, say, mussel shells. This shouldn't be the case, because they would not have any action when inserted into the real biomass. They are not really biomass, they are biodegradable, but in a very long time. So even if you incinerate biomass, you need to go up very much into temperature, if you want to produce a sufficient amount of energy, this is not proper biomass. So this will be explained later on, also in the seminars, which will be after Easter, about energy production and the different impact of energy produced in different ways. Then coming back to biodegradable, once you have a sufficient speed, sufficient velocity of biodegradation, and your biodegradation occurs at this velocity in a pH interval which is suitable and compatible with soil, then you can consider your material compostable. Also in this case, there might be quite some differences. For example, there is the question of the different ways of composting materials. You may have compost piles, which is the most brutal and simple way to producing compost. Compost maturing, so preparing for action. Compost is prepared for action for quite some time before to be put into soil. And you can have some more complicated way of composting, for example, composting systems arranged into floors. So you may have different floors, different layers of compost, which are matured at different velocities for different pH applications, also different acidities of the soil, etc. And also at a higher velocity. So you may have compostable polymers which are compatible with a compostability test, because of course the polymer, before it comes at the end of life, even before we produce it, we need to ensure that it is compostable. So there are compostability tests which are performed at a some defined temperature, some defined pH conditions, and we check that the velocity is compatible with what we want to do when inserted into compost. Before it is marketed because it is imposed on the market, you need to make these compostability tests to be sure that you can consider it compostable. This is ensured if you look at plastic bags. This is ensured by the European norm, whose number is 13432, and this European norm gives you the precise indications of compostability of a polymer. In bioplastics, one of the terms which I introduced in the first seminar, in the introductory seminar, was the question of cradle to cradle. Cradle to cradle means that we start producing something from a raw material. This is referred to bioplastics produced from biodegradable material, so not produced from oil, not polycaprolactam. And the raw material is a biological material, so might be a derivative from polysaccharides. This is the most frequent option. And you have this kind of feedstock, which is the cradle, and you are able to come back to the production again of the products you collect. And this seems to be quite confusing, because what you can see is that you get some resins, some plastics or resins, and you produce, and there is some recycling process, which does not contradict what I was saying before. The question is that bioplastic, if it is used on its own, would be compostable. This slide doesn't say bioplastic, compostable bioplastic, because you can have a bioplastic which is obtained by renewable raw materials, so materials which are obtained from agriculture, basically, which is biodegradable, but not necessarily compostable. There are some bioplastics which are biodegradable, but not necessarily compostable. Plus, I don't have just this into the product. Into the production, I introduce some bioplastics, but I introduce also something else. For example, if it is not compostable, I can introduce some wood waste, for example. You have seen some bioplastics based on bamboo recently. Well, bioplastics based on bamboo, whatever they say, it's not compostable. It is biodegradable. Worst enough, they have done an experiment by digging a hole and putting some bamboo forks. You may have seen the images on the net. That well, of course, it's a trick. First of all, because you don't compost something by just digging a hole and putting it as a whole without any mechanical grinding. You always grind it to powder. Mechanical recycling is the first stage, and it's always performed. Even if you want to have compost, you have action. That recycling arrow means that there is some part which is not compostable, and I separate it. I separate it, for example, course, with a mechanical, of course, with a mechanical action, I have a mechanical action, and then I separate, for example, the wood particles from the rest, which might be done by filtering and so on. A part is compostable, and then I put into compost production, and another part is recyclable. From a mechanical point of view, for example, bamboo powder could be recyclable in a mechanical point of view. I can glue and make some wood plastic resins and so on. You see the confusion of all this. You see the mess, because here we are not talking about plastic bags, but we may be talking, for example, about bamboo cutlery. Bamboo cutlery is made of wood and something else. Bioplastics, for example, made still from bamboo, but bioplastics, not bamboo powder. So you may have bamboo plastics and bamboo powder. The bamboo plastics might be compostable. The bamboo powder is not, can be recycled. I hope it's not too confusing. The confusion doesn't depend on me. Well, I always assume my fault when it is the case, but in this case, we can see that the confusion is given by the fact that something which is biodegradable, it is seldom compostable. There are very few items which are biodegradable and compostable. You have seen plastic bags. They are compostable, then they comply to EN 13432 because their thickness is very low. Lots of complaints about this because they break by shear and so on. But the reality is that the old polyethylene bags were 100 microns thick because their requirement was to keep package your course, your food, what you were buying, and now they came down to 20 microns in order to make it compostable, to make the bags compostable. Because otherwise they wouldn't work at the right velocity, at the right pH, and in presence of acids, etc., within, and fertilizers, of course, within compost. Okay, so the whole cycle would take some time, quite some time, more than, of course, the agricultural time of a few months. It may take 1 to 10 years, because then the main question is that I have to produce some crops, plant some crops to produce bioplastics. This is not sustainable in the first place, because if I think about it, corn is something which I produce to be eaten, basically to be consumed or to be transformed into edible products, into comestible products. Instead, I used it for bioplastics, and this doesn't seem very fair in the first place. So that's why they are starting thinking about agricultural feedstocks which are not planted for the same purpose, for the very purpose to make bioplastics. For example, waste. Waste has no use anymore, or non-edible plants. I could produce starch even from non-edible plants. There is no reason why I should produce starch from plants that produce edible items, from food plants. There are a number of types of starches from cereals. There are some cereals which are not very interesting from the point of view of food consumption, and other ones which instead are more rentable in this term. So I could make choices. There are other problems related to corn, because corn tends to have a monoculture, tends to establish monocultures, and the yield of corn decreases from year to year because monoculture tends to make the plant more feeble, weaker, because it has no natural enemies and tends to become less performant, less gives less, giving less fruits, less yields, yield lower, yield is lower in the end, and so there is a number of there are a number of possibilities. Here it's also considered the part that some part of my packaging could be even burned for energetic recovery. I could consider, for example, that bamboo powder could be recycled into, say, furniture, but I could also consider that I burn bamboo powder because it's wood in the end, and I could burn it. I could put it in the stove and burn it. So you can see that the situation is complicated. We are not general consideration. We are not considering that we need to sort out the problems. We need to understand the method to evaluate some situations, the method to compare. And more than the numbers, because the numbers may change, yield of, say, corn crop may change. The amount of water needed to cultivate corn may change. What is important is that we have an idea of the order of magnitude of these numbers, and also we have an idea of the possible options and of the possible factors involved. That's why I presented you with this slide as well. I would like to speak for a few minutes and then stopping because I think we have already introduced a number of questions. So I would tend to stop on this one. This would be the last one I will present. Then I will complete the file number one in the end, in the next lecture, which is going to be on Wednesday. But apart from that, it is important that we realize one thing, that sustainability would like to improve best practices. I've done an example with the COVID-19, but that's the same concept. We would like to understand which is the best practice. Please be aware, the best practice in the specific situation. For example, the best practice in Camerino might be different from the best practice in Rome, even if the materials are the same. But for example, I may produce energy in one way or in another way to produce my plastic. This changes a lot the sustainability balance. So I need to consider the different factors in order to compare the practice. So sustainability, once I have decided which is the best practice, I need to reward people, factories, so companies, and the general community to do that. For example, well, one of the most obvious reward is that I give incentives, also in terms of money. For example, if I want to improve the system, the recycling system, I could take off the bill some money if you bring directly your plastics to the collection island, to the collection system, instead of asking me to come at your remote house in the countryside. If you bring the plastics to the collection center, I can decide that next month you will pay €5 less. That's an example, but it gives you an idea. Of course, reward can be also on another point, from another point of view. For example, you have this plastic. You say that you reuse it. You have an idea to reuse your plastic waste. I can give you for free some waste, and decide that I accept your idea to reuse it. You have an idea, for example, to reuse plastic bottles. This is a stupid example, but to give you an idea of what is involved. I can give it to you for free. I can come with a truck with 1,000 plastic bottles, and I accept that you are reusing, for example, in your allotment to repel birds or something like that. I can accept your idea because now the main question of Directive 98/2008 is that the European Union accepts that waste is a subjective matter, it's not an objective matter. Waste doesn't become waste anymore if you have an idea to reuse it. And but of course, this means the so-called extended responsibility. If you have an idea to reuse waste, then your idea should work, because otherwise there are penalties for that. Okay, then I need to measure the performance. How I assess that the plastic is the best one. I compare performances one against the other, and I can see that performance is measured against these three aspects. There is an opportunity for innovation. This is good in the sense that you say that the best practice is to use waste to produce plastic bags or plastic trays. That's good. This is an opportunity for innovation. You may create a company and therefore hire people and so on. This is good, and I accept that. It could be a competitive advantage, meaning that I could spend less. Also, the collection system, the council, the city council, town council, spends less to dispose of plastics because you make some compostable plastics, and for example, I spend less in transporting compost because you give me for free some compost from your compostable plastic. That can be interesting. And also in social terms, remember, if you have followed and waste management course, you may remember that social questions are mainly about our health, our way of living and our health. And so if I am able to avoid the risks, because of course, workers that produce plastics and that deal with, say, injection of polyethylene may undergo some risks. They may need some masks to work. They may need to work in an enclosed environment. This costs, and this may create some risks as well, casualties, etc. And if I am able to make a process, to establish a process which is less risky, then it is another reason, one of the three main reasons to have a better performance. So performance is measured against these three big objectives. The possibility to innovate, to make patents and so on, the advantage over competitors, and the fact that there are less casualties and less risk in general terms. The last thing that I wanted to say, then I will talk you a bit the material for the course, swapping to the last slide, is that, for example, you may have heard that material science, we are going to talk a lot about materials because this is the main point of sustainability. The fact that we produce material and we use some materials instead of others is more a question of material substitution. Material science deals a lot with materials replacement or substitution. What does it mean? It means that, for example, I use it to make bottles in glass. Then I use now bottles in plastics, in conventional plastics, and I could use bottles in bioplastics. These are the These have three different environmental impact. There is not any process which is without impact. And I can compare the three processes to assess which is the best practice, which is the best process if it is done in some place with some conditions. Because of course glass wouldn't be the best one in any case, or bioplastic wouldn't be the best one in any case. It depends where I am, who produces glass, from where glasses is transported, for example, in the case of glass, and what is the end of life of this glass, what I can do with glass. I can recycle glass, yes, of course, if someone takes it away and goes to the recycling system, etc. Or if glass is given back to the factory that washes it and put it again into filling the system with water. So it depends on the very situation. This is a study, this is a table from a study which was done in Southern America, and it was about replacing fiberglass, glass fiber composite, so composite made with glass and some resin, usually in most cases a thermosetting resin. Instead of glass, they were thinking to put some Kurawa fibers. Kurawa is a plant which has also some food-related uses, but it produces some fibers, and you could replace glass by that fiber, of course, provided the weight they withstand it's about the same. They usually start doing this kind of replacement with kind of cosmetic, what engineers call cosmetic parts. A cosmetic part in a car is not a part for cosmetics. It's a part which is not an essential part. A wheel is not cosmetic in a part because a car without wheel wouldn't work. But a panel, an internal door panel, is cosmetic in the sense that we need a door panel, but even if we don't have the internal door panel, or even if it is less resistant, the car would work anyway. So they start with some caution. They tend to be prudent about that. And as always, since sustainability has these three aspects: economical aspect, environmental, and social aspect, there are these three lines in the table that represent these three characteristics of sustainability. There are some opportunities because Kurawa, for example, is for free. The problem with Kurawa would be, well, so it's better to substitute glass with Kurawa. In principle, yes. The question is that every plant has got its season and its seasonality, which means that I may get Kurawa fibers at some time during the year, but not over the whole year. So I may need to import them. It's like for, say, oranges. We assume now that down the supermarket at every time we are going to find oranges. The reality is that oranges have a definite season. If it is not the right season, I have to import oranges. With Kurawa fiber, it's better than with oranges because oranges get mold if full of mold. If I can put can maintain them into a store for some time. I cannot keep oranges in a store for 6 months. I can keep Kurawa fiber in a store for a few months, so I can, even if the season is completed, I can keeping them in store for some months, protect them, and they will work anyway. The problem is that costs. That means I need to have a store that have some economical consequences and so on. I may consider, for example, stock building, and build a store to stock them, or to have it from multiple suppliers. For example, yes, some automotive industries have started to use again natural fibers like flax or hemp, but they prefer buy them at the right time and season, even from the other side of the world, instead creating some stores with people inside, and so economically some economic burden and so on. So there are some questions to be considered. Of course, there is the aspect of mechanical performance and so on, health risks in terms of social performance. The problem with Kurawa with respect to glass is that I can produce glass down the road. Instead, if I import Kurawa from another country on the other side of the world, I cannot control which kind of conditions are the workers working on the other side of the world, which doesn't involve, which might not always involve environmental conditions, but it involves social conditions and the possibility of having some casualties and so on. For example, they tend to natural fibers are going to be treated to make them stronger with alkalis, with sodium hydroxide. There are some countries in the world, around the world, where sodium hydroxide is still applied without any caution, without any masks, any protection, like we were doing in Italy in the 30s or so. And of course, the producer, I mean the automotive producer in this case, should be responsible also for that. That's why this is an ideal, because they usually, till now, they haven't cared much. But the extent of producer responsibility means that I need to ensure not only my workers need to be safe, but also workers in other places of the world that produce the raw materials I need to complete the product should be safe and as free as much from risks, from health risks. So you understand that the question can be complex and so on. I would say that I'll stop in a few minutes, and therefore I get, as I was saying, to the last slide. We will complete the rest of it on Wednesday. So I will supply you the slides of the course. So number 1 and number 2, I will put them on my page. If you have not access to my page, please email me. It would be better if you email me, so I can give you the PDF I have for this course. So the book, which is a handbook of sustainable development, which is very general, and it is a number of chapters on different subjects, which all are connected with sustainable development. And this is the textbook, which makes you aware of different aspects, different phases of sustainable development. Then we have some papers. The first one came out in 1995, so close to the Brundtland report, and it is important to read it because it gives you an idea of what is the history behind the environmental sustainability concept. Some of the things that Goodland says are possibly overcome by reality, but it's important to understand how was the birth of the philosophical concept of environmental sustainability, which, as I was saying last time, is connected with the fact that we are aware now that our resources are not infinite and we need to keep the environment for future generations and for ourselves, of course. This is the starting point. Then it has been articulated in a number of different concepts and of aspects. Then there are other two papers. One is connected with steel. Steel, it's one of the material that has been prepared for end-of-waste strategies. And it is a very recent review that means that it's review. It's the collection of papers, so an explanation of papers, or different papers on steel, because steel they are starting to prepare for end of waste strategies. We have end of waste strategies just for copper, and we are starting to have it for inert materials and for especially for and also for rare earth and so on. But still, it's in the pipeline now for end of waste strategies. And then we have the question of microplastics. The last one, it's about microplastics from the textile industry. So microplastics that come down the washing machine, basically, in most cases, and which is a big problem, and it's important to be aware of it. This review as well, it's a very recent one. Since someone was asking, my email, it's carlo.santulli@unicam.it, so name.surname. And you will have the sustainability file number 1. This is the number 2, which we will complete in on Wednesday, and these course materials, and then the recording, which I'll put also on even on Facebook, I think, of this lecture, which is number 2. And I have already number 1. Please feel free to write. I think that's all for now. We will see again on Wednesday at 2. Thank you. Have a nice day.